Hello. We're going to be talking about Chapter 9 in Solomons. So this is having to do with NMR and mass spectrometry. So this chapter is really going to be about how do we know we've made what it is that we think we've made. So NMR is used to primarily look for structure. So how are the atoms arranged in space? And mass spectrometry is actually used in to determining the mass, the molecular formula for the compound. And so these are two of the machines, right? So this is an NMR. It kind of looks like a really big R2D2. So this is actually this is the mass spectrometry here. This is actually UPLC. So this is used for separation, And so as your complex mixture separates, each one of those individual components can get run through this machine here, which determines its mass. So NMR is up first. So it's a giant superconducting magnet. In here, you've got coils of wire, so miles and miles of these sort of hair-thin wires going around this this sort of sample tube. It's to make it superconducting. It's bathed in a pool of liquid helium, so at about 4 degrees Kelvin. So outside of that, because helium's really expensive, it usually has liquid nitrogen on the outside to keep it cold, so to help insulate it, because nitrogen is pretty cheap. So your sample is going to go in. So it's usually in a tube like this. It's a thin-walled tube. It's perfectly straight because it'll spin in there, and if it weren't straight, you get a little bit of a wobble, and so it could distort your signal if not. But it's just you just need maybe that much sample, just maybe half a milligram, maybe fine in solvent. But it goes into the depth of the machine, and then you send radio waves through it, through the sample, and then you get these little signals, these little peaks here. So they're coming up from the baseline. So what happens with this? The reason why we put this in this giant magnet is the fact that a nucleus, right? So it's going to be spinning. So when electrical charge spins, it'll give off a magnetic field. And so we talk about there's two ways that it could spin. It could either spin up or spin down. So, and when it does this, so that if there's no magnetic field around, okay, the poles for the magnetic field from the nucleus is going to sort of randomly. So you can sort of think of like boats in a lake, right? They're all kind of meandering everywhere. As soon as you put them in a magnetic field, they're going to go they're going to go straight up or straight down. So now you're talking about boats in a river, right? So they're either going to go upstream or downstream. Okay, so if you're going to go with the current, right? So let's say the magnetic field is pointed that way, it's going to be a lot easier to go downstream with the current, right? It's just a lot easier to do because the current will just take you. However, the other option is to go against the magnetic field, so go upstream against the current. That's fine, but it's going to cost you a little bit more energy to do that. But you're going to get a distribution of these two. Okay, possible states. So what happens is you send a photon in radio frequency, right? Or you send a photon in. And what you're looking for is this photon. If it has the correct energy, it'll actually bump the sort of like sort of up into a down state. So there's a gap here, and so that gap is going to correspond to that to the energy of the photon you put in. So since you know what you put in, right? So that you can measure that, and so eventually what's going to happen is it's going to say, well, I'm in too high of an energy. I'm going to go back down, and then it's going to release a photon, and that difference is what you see here, right? So the photon that's released is going to be your chemical signal. Okay. Now the only thing is not every nuclei is actually magnetic. Not every nuclei can be able to do this. So what you need in order to be able to do this technique, okay, is to be able to look at the the atoms with this technique, is you actually have to have this magnetic nuclei, okay, in order to be able to have this up-down. It turns out you either need to have an odd number of protons or an odd number of neutrons. It doesn't matter which one. As long as you satisfy one of those criteria, you're good. So hydrogen's great, right? It has one proton. It's odd, so you're good. So yes, fluorine is another one, right? So that has 9 protons. That's fine. So it does this. Doesn't matter if these are even. Doesn't matter. Just as long as you satisfy one of those 2 rules, you're good. If you satisfy both, that's fine too. But something like oxygen, right? It has 8 protons, 8 neutrons, right? 16, I should say. It is not magnetic. Okay, so you can't use an NMR to look at oxygen 16. How about that? So, and so some are, some aren't, right? So all the odd number of all the atoms with odd number of protons, right? Those are automatically going to be the magnetic, right? Something like that. But the even ones may or may not be. You just have to figure out how many neutrons they've got. Okay, so what's going to happen is, how about that? So I know this says 16. Oh, by the way, I forgot to mention this. I know it says 16. So about that. So those actually correspond to a different book. I wasn't entirely happy how the Solomon's did it. We're going to be incorporating that stuff in there, but I think it sped too quickly through the material. So about that. So I'm going to be slowing it down and using some slides from a different book. So about that. So it's the same material. It's just going to be presented in slightly in more detail. So about that. So okay. So one of the things that happens with this is that the different atoms within signals. So if you're talking about hydrogen NMR, okay, you can only look at the one atom type at a time. Okay, so if you're doing hydrogen NMR, you're going to be only looking at hydrogen. If you're doing carbon NMR, you're only looking at the carbons. If you're doing fluorine NMR, all you're going to see is the fluorines in the molecule. Everything else is going to be blind. So you have to focus on just one atom type at a time. Okay, so if you're looking at the molecule and different signals in spectrum, so if they're what are called heterotopic, they're in slightly different chemical environments, so they're going to give different signals. Okay, if the atoms reside, in the same chemical environment, right, they're going to give the same signal. Okay, either they're going to be clumped together, or they're going to basically be stacked on top of each other. Like that, they're going to be. So the reason for this is the fact that you know what the standard magnetic field is going to be, but the problem is, so that's going to be your applied the external field. Okay, but remember, you've got all these little magnetic nuclei going around in the atom, stuff like that, and so they are interacting with the atoms. So one particular atom is going to feel the effects of all those other magnetic fields. It's either a large magnetic field, or say it's electronegative, so it's pulling electron density away, so it's pulling insulation away from it, so it's feeling the applied fields of it. And so those very subtle differences are what we pick up. That's what's called the chemical shift, is how far away are you from that applied external field. So how far have you been shifted? So if you're what are called shielded, that means that the nucleus that you're looking at, that particular atom, isn't feeling the applied external field. It actually has a very small number for the chemical shift. For deshielded means that it's feeling it quite a bit. It's feeling that applied magnetic field quite a bit, and so it has a lot less insulation around it, and so that's going to have a higher number. Okay. So like that, and so like here, so that with the benzene, right? So all of these hydrogens are in the same environment, right? So chemical environment, right? So they're going to be here, but this benzene, this actually shifts it quite a bit, stuff like that. So, but you're going to get a signal here. Everything is references to trimethylsilane, stuff like that. So that's just that's an external standard. So you just put you get a bottle of your solvent, and you put a drop of this in there, and so you have a little bit in there each time, and so you mark that as at the 0 point, and so it's all relative to this trimethylsilane, the signal. stuff like that. So for here, this is the chemical shift. So this has been shifted down. So this parts per million, we'll talk about this in a second, what that means. But for hydrogen NMR, it usually goes from about 0 to 12, 14, somewhere in there. Stuff like that. So, okay, and so if the hydrogens are in different chemical environments, right, they're going to give different signals. So this one's carboxylic acid, right? This hydrogen's on a carboxylic acid, so it's going to be shifted down here. Oop. With that, it's going to be in a much different environment than having a hydrogen off of an alkyne here, and so this one's going to give a different peak, so it's down. So it's right here. So again, with this TMS reference signal at 0. Okay, so the question becomes, how do we know if they're different in different environments? Okay, and so what you do is you say, okay, if I were to redraw the molecule, okay, so where I put, substitute for just one of the X's, so all the different combinations, where I'm going to put an X in for each one of those hydrogens. Okay, so what's the relationship between, if you're going to compare the two molecules, either if they're the same or they're enantiomers, that means that those two particular hydrogens are equivalent to each other. Okay, so they're going to act like one. Look at that. So if instead they're just constitutional isomers or result in diastereomers, then they're going to give different signals. Okay, so by that, so this is what I say. So here, if you're going to, so there's 6 different combinations where if you just say like, okay, I'm going to put an X here, on this molecule, put an X here, this molecule X here, and then go all the way around. So by that, so these are all the same molecule, right? Because I can just rotate this molecule in order to make this turn into this. I could take this one and rotate it and make it turn into that. And so I can get that hydrogen to all the other positions and the molecule still looks the same, or it's an enantiomer. So like that. And so that's why all of those hydrogens are give a single signal, right? Because they're all equivalent to each other. Okay, so they act like one big hydrogen, right? So like one big CH6 group. However, okay, so molecules aren't typically like that, so there's something like this. So if you have something like propyl chloride, like that. So if we compare, say, these 3, okay, so we would put the X here, or X here, right? So like that. So those, right? So put it here, here, or here, right? Notice how you can just rotate the molecule and get it back to looking. I can just rotate this bond here and get it back to look like this. Same thing here. I can just rotate around that bond and get it back to looking like this. So that means that these red X's, all 3 of those hydrogens are equivalent to each other. So so those 3 are going to be represented by one signal. With the blue ones, right? So with that, so from here to here, the difference between these 2 are actually they are enantiomers of each other. Okay, so that's fine. That means that they're going to be represented by one signal. Okay, and here again, this is just like this, where you can just kind of rotate the molecule and have these 2 be equivalent here. So like that. So because you can just rotate this to make this look like that. So the or actually take that back. They're actually enantiomers of each other. So like that. So because this is right. Here's your 4 groups, right? Ethyl, propyl, hydrogen, X. So with that, so these would be enantiomers of each other. So again, they're going to give a single signal. So you're going to have 3 signals in this molecule. One that corresponds to the red X, one that corresponds to the blue X's, and one that corresponds to the green X's. Okay. Now, the other thing that you have to do is you have to be careful about, particularly for double bonds, because remember, you can't get free rotation around them. Okay, so like that. So for this right here, so vinyl chloride, so like that. So the what is it? If you put each one of these hydrogens are actually distinct. So even though these hydrogens are on the same carbon, they're going to be distinct. So there's no way that I can rotate the molecule. So if I were to take the molecule and flip it like this, now the chlorine would be up here, and so the molecule isn't the same. You can also think about the fact that because you can't get free rotation here, this blue X here really only is only going to feel that this hydrogen here. This X, the green X here, is really going to feel this chlorine here. It's certainly a lot more than this one here is pointed away from it. So they're feeling this chlorine differently. So they're going to actually give two different signals. So so there's three hydrogens here, and so you're actually going to get three distinct signals: one for the red, one for the blue, and one for the green. Okay. So the other thing, yes. So if you can make the mirror image, remember you can rotate bonds, you can flip the molecule. You can't like rearrange, break bonds or whatever, but if you can rotate the molecule, you can. So even if they're on different carbons, you can still be equivalent to each other, right? So this HC and HD, so those two are equivalent, because if I just rotate the molecule like this, right, the molecule still stays the same, and so those two are actually going to be equivalent to each other. Okay, so you don't even have to be on the same carbon in order to be able to do that, in order to be able to have equivalent hydrogens, because if because you have this sort of weird sort of symmetry in the molecule, you can just flip it over and it would stay the same. Okay. Now, one of the things that happens with this, and it can be both good and bad, that the time scales, because we're dealing with radio waves, things like that, low energy, NMR is very slow relative to the rotation of a bond of a regular like methyl group, and so what happens is that signal ends up getting sort of smeared out, and so you can't see within the three. You really can't, like here, here, and here, you can't see the distinct, right? They sort of run all around, or they're sort of whirling around, and so they just look like a smear, stuff like that, and so you only see the one signal as opposed to the three individual hydrogens. Stuff like that. So that can be good. Stuff like that. Stuff like that, because you don't have to worry about this, a bunch of weird signals that if they're interconverting. However, if you need to see it, right? So if you have it, this is the famous case is the cyclohexane, right? So you have axial and equatorial, stuff like that, and so those are in different chemical environments, right? So this is feeling the axial hydrogens here. This is equatorial, but it'll switch quickly, stuff like that, and so you'll get this the chair flip, stuff like that. The chair flip goes quickly, so it's seeing. So all you would see is sort of the average of the two, stuff like that. However, so the question becomes, how the heck do you, if you need to see which one's the equatorial and the axial? Okay, so what do you do? Stuff like that. So how do you slow things down? Stuff like that. So what you do chemically is to cool it and stuff like that. And so I pulled this picture here. So at 0 degrees C, right, the chair flip is quite quick. So you're only going to get one signal. But as you cool it down, the chair flipping gets closer to the time scale of the NMR and stuff like that. And so you're starting to see these two peaks pull apart, stuff like that. So at minus 78, minus 90, at minus 90, it's the chair flipping is incredibly slow, stuff like that. There's just not enough energy to get over that activation barrier, stuff like that. And so so you can see they're held fast, and so you can see the individual peaks. So if you want to actually see those peaks resolved, the thing to do is to cool down the sample and run it at cryogenic temperatures. Okay, so with chemical shifts, we already sort of talked about this, shielded versus deshielded. Sometimes you talk about the, if you're at a very low number, you call that upfield. The deshielded is downfield, right? So deshielded D, downfield D, stuff like that. So that means it's a high number. And remember, it's all relative to that. You'll see it as parts per million. Sometimes you see it as a little lowercase delta. Stuff like that. You can do it either way. The nice thing about this is that the chemical shifts are in fact independent. So usually what we're doing is a lot of times if you're talking to a sales rep or whatever it is, sometimes they'll talk about the actual Tesla of the magnet, stuff like that. But those are sort of like 15.4 or whatever it is, stuff like that. Those are a little hard to keep track of. So what they actually do is they actually typically refer to the operating frequency. That's a much easier sort of number to think about, stuff like that. And so you typically range anywhere between 60 megahertz and 1,000 megahertz or gigahertz, something like that. And so, sort of as you, and we'll talk about that in a minute, that's typically what people talk about for the more powerful the machine, the higher the frequency. Okay, so with that, and so this is where the chemical, but the chemical shifts are independent of the NMR type. So if you run in a 60 NMR, 60 megahertz NMR, that peak will be at that peak will be at 2 parts per million. If you run it in a gigahertz NMR, it's still going to be at a 2 parts per million. Okay, so with that, and so the chemical shifts, you typically see this. This is the chart I'll give you on the test. You don't need to memorize it, but just be familiar with it. Stuff like that. So as you typically what's happening is the closer you are to something that's electronegative, stuff like that, the farther it pushes down, the higher the number, the further downfield it goes. So alkanes are here, stuff like that. So if you're next to something electronegative, sort of a halide or an OH group, stuff like that. Now this doesn't matter if it's a CH, CH2, CH3. It'll still sort of be in this 2 to 3 range. So, but again, it's right next to something electronegative. We'll talk about these in a second. But notice how these are C double bond O is right next to that big old oxygen, that or hanging off an oxygen. So see that. So with that, so you do get what are called inductive effects. So with that, and so as you're starting to get more electronegative things on there, that number goes up, right? Carbon-carbon double bond versus a carbon-oxygen double bond is going to push that further downfield to a higher number. So the more electronegative things you have, again, shift it further to further downfield to a higher number. Okay, now benzene and is kind of a weird case. So like that, because remember you've got the delocalized electrons whirling around here. Whenever you have an electrical charge going in circles, right, you're gonna make an electrical field, right? So what happens is you have not only the magnetic field of the magnet, and you have the magnetic field of the little environment, microenvironment of the atoms neighboring it. But the signal will also be feeling the magnetic field of the benzene ring itself, and so that really pushes it down. So they're sort of fingerprint region in this sort of 6 to 8 region. If you see that, you're going to be, it's really downfield. That's going to be a benzene. It's pretty much just about the only thing down there. You do see this with just regular double and triple bonds. Not so much with triple, but definitely with double bonds. Stuff like that. So again, you have the circular motion. It's just not quite of a big of effect, which you can see here, where if you're next to just a regular alkene, it's shifted down to sort of this 4 to 6 region here. Stuff like that, particularly the 5 to 6 region. Stuff like that. So just be aware. Now these effects are cumulative, right? So if you were to have just a regular alkane, it would be at 0.9, but if you had 1 chlorine on here, it's 3.1. If you had 2 chlorines next to that hydrogen, it's 5.3. But notice it's not additive, it's more cumulative, right? So that so if you have multiple effects, it could shift it beyond what those what the normal ranges of the chemical shifts, stuff like that, and that could be because multiple things are hitting it. It won't be a one-to-one addition, stuff like that, but it is a cumulative effect. Okay. Now, the further away you are from that electronegative thing, the less it feels. So if you're directly on, so this is causing things to go downfield, stuff like that. And so if you're directly on the benzene, and you're at 7.2. If you're next to the directly next to it, you're still at 2.6. Okay, but if you're 2 carbons away, you're down here about 1.2, which is pretty normal for maybe a little bit downfield, but not nearly as much as these two. So as you go farther away from the ring, you don't feel it nearly as much. Okay, so the signal itself, the nice thing about hydrogen NMR is if you take the area under the curve, stuff like that, so you do your calculus, whatever it is, the area is relative to how many hydrogens are represented in that peak. Okay, so this peak here is actually representative of these 4 hydrogens here are equivalent to each other. So this signal would integrate to 4 hydrogens. These two methyl groups are actually equivalent to each other because you can just flip the molecule like that. So this would integrate to 6 hydrogens. Now, what you end up doing is you get a ratio. So it's actually like it would be 4 to 6, but really what you would see initially would be 2 to 3. So this is, or 1 and 1.5, stuff like that. And so what you're looking for is, notice this blue line here, that height, that's doing the sort of cumulative hydrogens, whatever. That height, you look at the ratio of the height of this blue line here, this one here to that one there. So with that, and so this is 50% higher. This sort of ledge here is about 50% higher than this one. So for that, because it's 6 to 4. Okay, so you can sort of see it sometimes as one, two things. You either can get it as a regular sort of, like if you had, let's say we had an NMR with 3 peaks, and the ratio was 1 to 3 to 6. Okay, so with that, and so you look at the chemical formula, right? You say, oh, there's 10. I know that there's 10 hydrogens in there. Well, we can account for all 10 of those. Not too bad. So with that, so let's say you take another compound, do the NMR on it. So you know the formula has 16 hydrogens, but the ratios come out 1.5 to 2.5 to 4. Well, you can't have half a hydrogen, right? So about that, and so what you do, these are just reduced ratios, and so what you can do is just multiply everything by 2, right? It's just like 4 to 6 is the same as 2 to 3, right? You just multiply everything by 2, and so it ends up being 3 to 5 to 8, stuff like that, and so that makes sense because now you've got your 16 hydrogens to account for. As long as you multiply everything by the same number, you're good. You'll maintain that ratio. I'm going to show it as sort of expanded ratios like this, so there's no confusion. So with that, but sometimes you see it like this, so you have to be aware. Okay, so this tells you, so the integration is going to tell you how many hydrogens are represented by that signal. Okay. The splitting pattern, now this is one of the weirder concepts. The splitting pattern will actually tell you how many neighbors are next door. Okay, so about that, and it's this n+1 rule, so the neighbor plus 1 rule. Okay, so so this carbon here, right? It has this 1 hydrogen here. Okay, it's in a different chemical environment than this one, right? Because this carbon has 2 chlorines. This one only has 1. So this hydrogen, okay, so it's going to integrate to one hydrogen. Okay, so with that, so but it has 2 neighbors, and then they have to be directly next door. Okay, with that, so this one has 2 neighbors, 2 neighboring hydrogens. Okay, so it's going to be, right? So you're talking about n+1, right? So with that, so if you have 2 neighbors, it's going to be 2 plus 1. So it's going to 3. So it's going to turn into a triplet. Okay, so 1, 2, 3. This one here, right? So with that, so it's going to integrate to 2 hydrogens. Okay, from the previous one. So with that, but it only has 1 neighbor to it. Okay, so 1 plus 1. Okay, so with that, so it's going to be 2. So we call that a doublet. Okay, so there's 2. Okay, so you have a triplet and a doublet. The integration and the splitting are completely separate. Okay, so with that, so don't confuse the two. Integration tells you how many are on there. Splitting tells you how many are next door. Okay, so with that, and so so if you have no hydrogens next door, okay, so 0 plus 1 is going to give you 1. We call that a singlet. 1 to get doublet, and then triplet, quartet, quintet. Now multiplet means we just don't know. So like that, or it's a mess. It's a whole bunch of like things on top of each other. So like that, but you can have a what was that? A sextet. So for that, sextet, septet, octet. Usually, if you go beyond octet, you either have a multiplet or you just say like 9 mer or 10 mer or something like that. So but remember, it's neighbors plus 1. So okay, so we ask how many neighbors are on here, right? So it's you have a doublet, right? So what plus 1 equals 2? Well, that better be 1. Okay, so with that, so 2, right? So this one is a constant, right? So for that, so how many? So we're solving for the n. Here it's 1, 2, 3, 4, 5, right? So with that, and so what plus 1 equals 5? Well, that better be 4. So with that here, if there's one signal, so what plus 1 equals 1, well, then you have 0 neighbors. Okay, so remember the splitting is going to be talking about neighbors. Okay, now the splitting patterns, right? So with that, so chemically equivalent hydrogens are not going to split. Okay, so these guys are not going to split each, wouldn't be able to split each other. But the important thing is these two guys here, these two hydrogens are chemically equivalent to each other. They are right next door to each other, but they do not split each other. Okay, so with that, so they're still going to get just a singlet because how many non-equivalent ones are next door? So, okay. But these, right? So these, and these, right? So these act. So OHs and NH, it really depends. So with that, so it depends on what solvent you're using. Sometimes it's a broad peak. Sometimes it's a it's a normal peak. So with that, and so you just have to sort of be careful. So with that, and so this one is. So if this is becoming a broad peak, you can sometimes ignore it. If it's not a broad peak, then you have to take into account it. So it's really solvent dependent. With that, sometimes it's there, sometimes it's not. With that, so for this book, they talked about how you can ignore it. In the Solomon's book, they talk about how you don't ignore it. So with that, and so it's sort of a case by case thing. So just be careful. So okay, so we talked about the resolution. So for that, the operating frequency of these things, and the fact that the chemical shift is going to be the same no matter if you have a 60 megahertz or 600 megahertz. So for that, and so there's a huge disparity in the price, right? So you can get a 60 megahertz machine for about $50,000. You get a 400 megahertz machine for roughly $400,000. But as you get higher and higher, so it usually ends up being like the old rate was about $1,000 a hertz. So at that, so or $1,000 a megahertz, excuse me. Stuff like that. But as you get higher, that trend accelerates. Stuff like that. And so if you're at 600 megahertz machine, you're more at like 1.2 million. If you're at gigahertz level, so there's only 2 manufacturers in the world anyway, but the one of them has a gigahertz machine, and it's like like $10 million or something like that. So it's really expensive. So why do we do this? Why do we care? Well, it's all about better resolution. Okay, but again, the chemical shifts are going to be independent, but the resolution. So you can think about megapixels on a camera, right? If you take a picture of Aunt Bertha on a 1 megapixel camera, it still looks like Aunt Bertha. If you take if you do a 10 megapixel camera, right, it's still going to look like Aunt Bertha, but you're going to get much finer details on the mole on her cheek, right? Stuff like that. So that's what you're looking for, and stuff like that. And so if you look in here, right, so if you get overlap, where it comes in is overlapping signals. So in a 90 megahertz machine, it's going to look like this, but on a 300 megahertz machine, you're actually going to be able to separate out these two triplets here. Here, they're sort of smashed on top of each other. So even though the signals are it gives the same signal, it's a much finer signal, and so you can see better resolution. Okay, so with that, so these aren't resolved well. So with that, but on the 300 megahertz machine, because it has a bigger magnet, you're able to narrow those the gaps a bit. So with that, so. Okay, and this becomes important if you're looking at very complex molecules. So this is a hydrogen protein, hydrogen NMR on a protein, right? So if you think about all the hydrogens on a protein, stuff like that. So even on a 600 megahertz machine, it still looks like this, stuff like that. And so I can't imagine what it'd be like on a 90 megahertz machine to be like one big, big blob. Stuff like that, and so that's why we need these. Now the nice thing is they don't go bad, right? You can use them for 10 or 15 years without any problem, especially if they're well maintained, stuff like that. And so if you're doing this a lot, the investment makes sense, stuff like that. So it's not a one-off disposable, item, stuff like that. So it works out well. Now, one of the things, remember we talked about the gap between here, there's the gap between the peaks. So like the gaps between the peaks in a doublet or a quartet or something like that. That distance is what's called the coupling constant. stuff like that. And it turns out that things that are splitting each other will have the same coupling constant, right? Stuff like that. And so C and D here, okay, they're splitting each other, right, in this ethyl, right? So with that, and so they're going to have the same gap, okay? These two guys are splitting each other. Now you see, what? I thought you said they weren't equivalent. No, they are. They're not equivalent anymore because you've broken the symmetry because there was a bromine here. So these two are equivalent, and these two are equivalent to each other. So like that. So these two guys are splitting each other. So the A's and the B's are going to have the same coupling constant. Okay, and so so if you're looking at which peaks are neighboring, right? So the 7-1 and 7-1, right? So these two must be splitting each other, and then these two must be splitting each other. Okay, so you can sort of start to get more information as to who is where by looking at that coupling constant. It's not a huge deal. It's one of those things that pops up like every once in a while. So like that. So sometimes it's given on tests, sometimes it's not. The molecules you're dealing with aren't. It's hard to you guys to believe, but they're not that complicated in that you need it. But as you start getting really big molecules, the coupling constants become more important. Okay. Now the problem is, what happens if you have two different things that can split? Okay, you have neighbors on one side, and you have neighbors on the other. Well, it turns out you don't pick; they actually both split. Okay, and stuff like that. And so what can happen is, so like this, like B here, okay, or A, right? It's got a neighbor here and it's got a neighbor here. They're both chemically distinct, right? So they're both going to split. Okay, stuff like that. And so this one, it gets split in. This signal A splits it into a doublet, but then C is actually going to split that doublet into another set of doublets. So you actually have a doublet of doublets. Okay, same thing here. So each one of these is going to be a doublet of doublets, stuff like that. And so the first one, now it doesn't really matter. Well, so you can either do split the C, this first, that into a doublet, and then this the A into a doublet, or you did the B, the A splitting first and then the C splitting first. It's really hard to predict which way it's going to go. This one doesn't matter. It's still going to be a doublet of doublets, stuff like that. But it makes a difference if it's, say, a triplet of doublets. We don't know. So this one here, okay, so this side is, I should say, this side splits it into a triplet, and then this side is going to split that triplet into I'm sorry, this one splits this into a doublet, and then this side splits those doublets into three. So it's a triplet of doublets. It's three doublets. It looks like this. Okay, so it could equally be as valid as saying, well, it's going to do a doublet of triplets. It's going to go. We're going to take this into a triplet, and then this is going to turn that into a sort of split that into two. So triplet of doublets, doublet of triplets. In practical terms, it doesn't matter. Stuff like that, because you can always just flip the order, and it doesn't make a difference because you're just saying on which one side I've got two, the other side I've got one, splitting it. Stuff like that. That's all it does. So, okay. Now, organic chemistry, right? It's all about carbon. Okay, so it'd be awesome if we could just do a carbon NMR. Okay, because nearly 99% of the carbon in the universe, or at least on this planet anyway, is carbon-12. Okay, so with that, so that's what we deal with every day. The problem is it has 6 protons, 6 neutrons, so it's not magnetic. So with that, but it turns out that the other two isotopes, carbon-14, that's not magnetic, right? Because it's 6 and 8. But carbon-13 is. So with that, it's about 1% of your signal. Okay, that is magnetics, and so we can take advantage of that 1% of the sample. 1% of the carbon atoms are going to naturally have this magnetic nuclei, so we can take a look at that. Okay, the problem is the signal, because you're only looking at 99% of the sample doesn't matter. You're only looking at that 1% that actually going to give a signal. A single signal itself is going to be very, very low. Okay, and so what you do in order to do this, you take a lot of signals. Okay, and so what's going to happen is, right, so you're going to say, like, well, here's the TMS, and actually the error it's supposed to be here. They kind of screwed this one up, but like, is that a signal? Those are probably signals, but and then this is solvent, we know that. But like this one here, is that a signal? Don't know. So with that, so it could, is that a signal? Well, we don't know. stuff like that. And so what you do is you add a bunch and then you average them. Okay, the real signals will keep being additive, but the non-signals will not. After a while they're going to go to 0. Okay, so the classic example is a game, coin flip game. So if I flip a coin, you get what is it? Every time it goes heads, I give you $1, right? So with that, so you win $1. Every time it's tails, I win $1, right? So with that, and so if we flip it, say 1,000,000 times, assuming it's a fair coin, right? On average, right? Neither one of us is really going to win, right? Because half the time you're going to win, half the time I'm going to win. We're both going to have $500,000. Nobody's going to win. So net effect is 0, right? But if instead it's always additive, so if I flip a coin on head, if it's heads, you win $1, and tails, you win $1, right? At the end, it's going to be 1,000,000 to 1, right? Or 1,000,000 to 0. Right, so with that, and so you are always going to add signal, right? You're always going to get $1 for every time we do the game. Same thing here. Every time we do a reading, right? So with that, so these actual signals will add a little bit more to it, but these spurious sort of signals, okay, will eventually, if you give enough time, will go to 0, and so they end up like this. But this is both good and bad. Because carbon-13 is in such low abundance, the likelihood of all of them, unless you put them in there, the likelihood of there being a whole lot of carbon-13s right next to each other is basically nil. Stuff like that. So it's astronomically low. And so what we can sort of assume is that every carbon-13 is just by itself. Right, so with that, so in the molecule, so with that, so and so you don't have to deal with splitting, which works out well, because it makes it, well, it's good and bad. It makes it simpler, but then you don't know what the neighbors are, so you have to do a little bit more, it's simpler, but you don't have as much information. Okay, the way we do the signals for the carbon, remember for carbon NMR, we're only looking at the carbons. Stuff like that. So and so we think about the carbons the same way we did with equivalent hydrogens, right? So we put those X's in there. These guys here, there's no way that I can rotate the molecule to get this X into this position and have the molecule look the same, okay, or this. But here, these 3 X's here, I can just rotate around that bond, right? So with that, so I can just rotate those bonds and get these carbons here into that position. So you're going to have 1, 2, 3, and then the one signal that's corresponding to these 3 carbons. Okay. So the chemical shifts. So with that, did I talk about this? Yeah. The chemical shifts. Now this one, it goes from 0 to about 250. So the numbers are different, but the trends are the same. The more likely, the more electronegative thing you have, either on it or hanging off directly off that carbon or next door, so the more it's going to get shifted in here. So like this is down around here, 0 to say 30. You're talking about regular alkanes. If you're sort of in the 50 region, you either have a halide on it or near it. If you're in this region here into the 100 and above 100, between 100 and 150, you're probably part of a double bond, a carbon-carbon double bond. If you're above about 150, you're part of a carbon-oxygen double bond, something like that. So that's a distinctive fingerprint here. But the trends are the same with that. So again, I'm going to give you this chart for the test. You don't need to memorize it. Okay, so the chemical shifts, something like that. So here, right? So A, right? That's part of a C double bond. O, it's right next to an oxygen, right? So it's going to be shifted way down here. As you get farther away from that oxygen, right, the further it goes down here. So B and E, right? They're pretty far away from the oxygen, so they're not feeling it very much. D is starting to kind of feel it, maybe. Certainly C is, because it's right next door, so it's shifted further this way. Okay. Now, the nice thing about integration is because the abundance is so low, the integration is basically meaningless. You can get sort of ballpark estimates, so at that, but for the most part, you don't have to worry about integration. Okay, so now the question becomes, how do we solve these things? And so one of the techniques that you can use is actually what's called DEPT, which is distortionless enhancement by polarization transfer. Okay, and basically what it's saying is how many hydrogens are hanging off of that carbon. Okay, so what you can do is you can take what's called a broadband signal or an uncoupled signal, and that'll just show you all the carbons in there. Okay, so if you have ethyl benzene here, so with that, so you've got this one, these two equivalent, these two equivalent. That's a signal, that's a signal, and then these two for the ethyl. Okay, so you're gonna have 1, 2, 3, 4 signals for the benzene, and then these two for the ethyl. Okay, so you're gonna have all 6 signals. Okay. Now for DEPT, if you run a DEPT-90, that's only gonna show the CHs. Okay, that's it. That's the only thing that shows up. If you have one hydrogen hanging off of it, it shows up in the DEPT-90. Okay. If you run a DEPT-135, you're going to have positive and negative signals, right? So notice how this one's negative right here. That one, the negatives are easy to see because it's CH2. Okay, but the positive shows both of all of the ones that have an odd number of hydrogens, so either CH or CH3. Okay, so the question becomes, well, if they could be CHs or CH3s, how do we know which one it is? Well, we already know which ones are the CH3s because we identified them in the DEPT-90. Okay, notice this one here only shows up in the DEPT-135, so it can't be a CH, so it has to be a CH3, because if it was a CH, it would show up over here, right, in the DEPT-90. So you can tell. The problem comes, well, what about the carbons that don't have any hydrogens on them? Well, they only appear in that broadband signal. They're not going to appear in the CH or in the DEPT spectrum, right? Because you have to have a hydrogen on there in order to get the DEPT signal, right? So we've talked about the CH3s, CH2s, CHs, but the Cs won't show up. Okay, you could have CH4, but that's just methane, and that's not going to do you any good. Okay, so how do you solve a carbon-13 structure, or a structure based on a carbon-13? So let me just write this down here so we can talk. So the broadband. So you're going to go through these steps each time. These are pretty good series of steps to do. 43.6, 15.4, and 137.8. Okay. The DEPT-90. Going to be 28.5, 7.8. The DEPT-135, right? You're going to have both the positive and the negative, right? So positive, negative. So 22.5, 28.5, 37.8, and this one is 43.6 and 115.4. Okay, so first thing to do is to just take a look at the formula. Okay, so C6H12. The problem is we have 6 carbons, but we have 1, 2, 3, 4, 5 signals. Okay, so 5 signals, but there's 6 carbons. So that's gonna indicate that we're probably gonna have something that's gonna be equivalent to each other. Well, it has to be, right? So like that. So if you have all of the carbon, if you have all the carbons accounted for, you have 6 carbons and you have 6 signals. Well, then they're all going to be unique. But if you don't, there's going to be some equivalency that you have to deal with. Okay. The next thing up is to just run a quick DOU. It's an easy thing to do and just to see what you're looking for. And so for here, it's right. So remember the formula down here. So it's 2 times the number of carbons, so it's 6 plus 2. That's a constant. There's no nitrogens, right? No halides. And then there's what, 12 hydrogens, right? So it's what, 14 minus 12 over 2. So this ends up being 1. So we have, we either have, remember a DOU is, it's either we have one ring, or for each one of these we have a ring or a pi bond. We don't know which. Okay, we know it has to be a carbon-carbon double bond because we don't have carbons, and it's only hydrocarbon. right? So if we had an oxygen here, it could be a CO double bond. So we have to be careful for that. We don't know yet. Okay. So then we go into the depth, stuff like that, and so we know. So the DEPT-90. So these are so this is going to be CHs, right? So we can identify, right? So this is going to be a CH. This is going to be a CH. Okay. For the 135, right? So with that, so this is for the positive, it's CH plus CH3. Okay, but we already know that this is a CH and that's a CH. So this has to be a CH3. So this right here, so CH3. Okay. For the negative, we know that these are CH2s. Okay, so this is a CH2 and that's a CH2. Okay, so we can account, right? So we know what each of those signals are. Okay, so not too bad. And notice everything's accounted for, right? Or at least we know what all of them are, so we don't have any C's. So that's just C's without any hydrogens on them. Now, what you can do at this point, I usually suggest going in and just seeing what you can account for. So you just add these parts up. So CH3, CH, CH2, CH2, CH. If you add those up, 1, 2, 3, 4, 5. So C5, H3, 4, 5, 6, 7, 8, 9, H9. So we can account for 5 carbons and 9 hydrogens, but this is our formula. So if we subtract out C6, H12, if we subtract out what we already know, what do we have left to figure out? Well, there's 1 carbon and there's 3 hydrogens, and notice that probably what we need to we can't account for is a CH3. Okay. Now, if you look up here, right, we do have the easiest way to do this is to say, oh, maybe what we've got really are is actually we have 2 of these. Okay. Now, if you had 2 different CH3 groups, you wouldn't know which one was equivalent yet. But since we only have 1 CH3, we know, well, we must have 2 of them to take into account. So since we can take, if we did 2 of these, right, we could get to our final formula. Okay. Now, last thing before we start putting the structure together is to take a look at the chemical shift. So you take a look at your chemical shift chart, look at that, and so you say like, okay, so these guys here, these are usually just regular alkanes, right? So with that, so this is pretty far downfield, particularly for a CH2. So this must be something. It's a downfield alkane, down alkane. So it must be near something electronegative. Okay. Now these guys here. Okay. So that's part of a carbon-carbon double bond. Okay, because that's the region for that. It could, you could say, well, what isn't a triple bond? Well, it couldn't be, because we don't have enough degrees of saturation. Okay, so we know that the molecule itself, right, has a CH2. Well, here, actually, let me draw this out. See, so we have a CH like that, like this. Okay, and so we know it has to have this, right? So one side of the carbon-carbon double bond has to have a CH2. The other side has to have a CH, okay? But notice what's going on here. This carbon has all 4 of its bonds accounted for, while this one only has 3. So this one has a bond where we don't know what's hanging off of it. So that means this has to be the end of a chain, right? We literally can't build anything off this side. If it was in the middle of the chain, it'd have to look like that, right? So this carbon, both of these carbons would have to have a CH3 hanging off of them. Okay, so with that, and so here we go. So with that, so this has to be the end of one of the chains. Okay, and notice how this one here, it's downfield. So that needs to be so with that next to this alkene, right? So with that, so right next to it has to be a C double bond O. Okay, so now how do we deal with this? Okay, so if we put a CH3 group in here, we're done. We don't have anywhere else to put this. But instead, if we put a CH group, well, then we still have 2 bonds that we can account for. And if we put the CH3 groups here, right, they can be, they are equivalent to each other. Okay, so with that, and they make the 4 bonds for here. So this is our structure here. Okay. Now, does it make sense? Well, okay, so we have a CH2 and a CH on our double bond. Okay, we have a CH2 next to it. We have two equivalent methyl groups down here, right? And then we have a CH group right there. It makes sense. If you go back and this doesn't make sense, there must be something slightly off with the molecule. Okay. Okay, so for hydrogen, for solving hydrogens, there's usually a couple things to do. Okay, so we're gonna be walking through. It's gonna be a very similar sort of process for the carbon NMR with some slight tweaks for the hydrogen NMR. So with that, and so where do we begin? So the first thing actually really to do is just take a look at the molecule, or take a look at the spectrum, take a look at the formula, and say, can we account for all that stuff? Can we account if you have 20 hydrogens but only 3 signals? You got to be aware that something's weird is going on. Okay, but if we have 5 carbons and 5 senses, if we had I should have said if we have 10 carbons but only 3 signals, then something weird's going on. But if we have 5 carbons and 5 sense signals, we may be okay, right? So with that, so it's not as clear cut as with the carbon case, but you can sort of take a quick check on equivalency. It's a really big rule of thumb, so there's lots of exceptions for this for the hydrogen, so with that. But it's never a bad idea to just take a quick assess the spectrum. So with that, so one of the first things that you can do is just do a quick DOU, so with that, just to know what you're up against. Okay, so run the DOU from the on the formula and see where you are. Again, you can see how many peaks, right? So that doesn't match the number of carbons. Maybe every carbon is unique. So with that, so if it is, there are some big exceptions for that. We'll talk about one in a minute. If not, then there's probably going to be some equivalency there. What do the peak integrations, do they account for all of the protons? If not, then we have to maybe multiply them all by 2 or 3, stuff like that. So certainly if there's there's 1.5, you're gonna have to multiply everything by 2, like that. So are there take a quick look at the chemical shifts. Okay, what are those telling you? Do you have those fingerprint regions? Do you have hydrogens in the aromatic region? Do you have them in the C double bond O? Do you have them in the aldehyde region? Stuff like that. So, what do those? Take a look at the splitting patterns, stuff like that. So if if coupling constants are provided, what's next to what, stuff like that. So, so here you go. So this is the type of you should see. I typically don't put an actual spectra on there because they're tiny, and there can be some it can be kind of hard to see sometimes. I don't want there to be any ambiguity on this, and so this is how I typically give them. 1 hydrogen doublet, and this is 5.54. And you'll notice I'm going to be doing all of these exactly the same way. And so if you do this the same way, you don't skip around. If you skip around, you're going to miss something. Okay. So here's the formula, right? So you have 3 carbons, 3 signals. So there may not be an equivalency, stuff like that. So that's a good sign. So first things first, right? We're running a quick DOU check, right? DOU is right. So 3 times 2. You have 3 carbons plus 2. We don't have any hydrogens or nitrogens. We do have a halide here though. So 1. And we do have 5 hydrogens, right? So 2. So if you do this, right? So 6, 7. Excuse me. Yes, I'm sorry. 6, 7, 8. Minus 6 is 2 over 2. So 1. So we have so we either have a pi bond, or a ring. Okay. So like that. And so next up, so just be aware of that. Okay, so the next up, we take a look at, I usually look what's in the parentheses here. So this is the integration, and this is the splitting pattern. So we know we have a CH3. Okay, so I usually circle it because we know that that's the bit we're doing it. But we're going to look to see what the neighbor is, right? So remember the neighbors are n plus 1. So what plus 1? A neighbors plus 1. So how many neighbors plus 1 would give 1? Well, it must be 0, so this needs to be a C. Okay, this one here, we know it's a CH. Okay, but next door, so with that neighbors, all right, so it's a doublet, so neighbors plus 1 equals 2, so neighbors must be 1, so CH. Same thing down here, so it's a CH, the CH next to it. Now, we're only putting together this CH3, this CH, and this CH, but we can kind of, but what's here is sort of showing you how you put the things together. Okay, so for that, what's next door? But these are the only bits that we actually have to worry about. So with that, so next up is you look at the chemical shifts, and so if you look at this, it looks like something, you know, sort of next to something electronegative, negative, or it could be, you know, C double bond C, you know, CH. It could be, so either, you know, it either has the bromine on it, or it's next to a double bond. Now these guys here in the 5 region, those are going to be part of a C double bond C. Okay, so but that's, so they're going to be part of an alkene. So that takes, so we don't have to worry about the ring. Okay, so you're going to have a carbon-carbon double bond. Okay, so there's really only 2 ways that you can do this, right? Okay, so with that, so we know they're in a chain, right? There's only 3, right? So we know, okay, so this is a CH, so we can do CH here, and then what's left is a CH3. Okay, notice that, you know, this has its 4 bonds known, this has its 4 bonds known, right? 1, 2, 3, 4. This one only has 3. We still have to deal with that bromine, right? So we can put the bromine here, and then there's our structure. Now, does it make sense? Okay, so this CH3, okay, well, it is next to that. The shift would say this, but how many neighbors does it have? Well, we're not allowed to have, you know, this one actually has 1 neighbor to it. So with that, so the splitting pattern was off. So this would, if this was the structure, this would be a doublet, and then this one here, it would be a doublet on this side, and then this would be a quartet, so it would be like a doublet of quartets, stuff like that. And so this splitting pattern is wrong. This one's right, stuff like that, but you know, it just simply can't be, stuff like that. And so the other possible way, right, because that CH3 has to be next to the double bond, right, so with that, is to actually put the hydrogens on the same side. Okay, and so that leaves the bromine here. The only spot available for that bromine is here. Okay, and you're going to say, well, what's going on? Remember, you can't get free rotation here. So this hydrogen and this hydrogen are in slightly different orientations. Right? So this one's feeling that bromine a lot more than this one is. This one's going to be feeling that methyl group, and so they're actually separate. So even though it had 3 signals, right, they're non-equivalent. So with that, and so this one here makes sense, right? So this CH3, how many neighbors does it have? There's no neighbors here, right? These guys are too far away. On this side, right, there's no hydrogen, so we're not going to get a signal from this one. Here, this one, that's a neighbor, so with that, so that'll split, but there's no neighbors over here. Same thing here, this is the only neighbor we've got. So this is the structure. Sorry, I should have gone through the slides. Okay, so here's another one. Okay. So C5H10O, right? So we have a 0.95. 6 hydrogen doublet. 2.10. 3 hydrogen singlet. 2. Septet. Okay, so that's a septet would be 7. Okay, so first thing, right, we have 5 carbons, right, and we have 3 signals. So something's up. Okay. Okay, so first things first, right, we're running a DOU, right? So it's right, so it's 2 times 5 plus 2. We don't have any nitrogens. Don't have any halides. Right, but we do have 10 hydrogens. Okay, so it's 10, 12, right? 12 minus 10, 2. This is going to be 1. Okay, so we have a ring or a pi bond. Okay, we just don't know which. Okay, so with that, so then we'll go in and take a look at this. Okay, so for this one here, so we know it's 6 equivalent hydrogens, right? So I usually write it as a CH6, right, in quotes. Okay, so it's 6 hydrogens working in concert. How many hydrogens are splitting it? Well, it must be a CH group that's splitting it. Okay. So for this one, it's a CH3, right? Because there's 3 hydrogens on here. But it's a singlet, right? Because remember, this is n plus 1, so what plus 1 equals 1? Well, neighbors, there can't be any neighboring hydrogens. So for here, CH, right? But here it's a septet. Well, it must be split by that 6 equivalent hydrogens. Okay, so for here, notice how these things are kind of lining up. So these are the bits we have to put together, right? And this is going to show you what's next, right? So with that, and so here we go. So this must be next to that. So we have a CH, and what's the easiest way to make six equivalent hydrogens? It's what you do is you have 2 CH3 groups. Okay, so that CH group must have, say, a CH3 here and a CH3 here. Okay, so since these are equivalent to each other, okay, they're going to act like a CH6 group, and then here. Now, we also have a CH3 group, right? So we could put that CH3 group there, but then that would make it equivalent here. But then we would be left with a C, because remember we have that extra just regular carbon, right? We also have to take this in. So we could put it like this, but the problem is, this one just has no hydrogen. But this, actually, the bigger issue is this methyl group here. That would have, right, 3, 4, 5 carbon or 5 bonds, which we can't do. Okay, so the other way that we could do it would have to be this. Okay, so we 1, 2, 3, 4, 5, right? So 3, 6, 9, 10 hydrogens, right? We still have the oxygen, right? And this still needs 2 bonds, but we have this 1 degree of unsaturation, so we can't make a carbon-carbon double bond. Okay, so for that, because this already has its 4 and this already has its 4, so we can't do that. So the way that we get around that is to put the double bond, the C double bond O here, and so this is our structure. So it's a little bit of a logic puzzle, right? So, I forgot to do this, right? I always forget to do the chemical chefs. So for here, notice how it's going to be pretty far away. It's just going to be in this sort of alkane region. But these right here, the 2 regions, okay, that's going to be next to a C double bond O, right? So this is going to be, so those are going to be CH, right? So it's going to be these guys next to a C double bond O, and this is just regular alkane. Anything below 1 is pretty much just alkane. Okay? So that's that. So there's your structure. Now for 2D NMRs, so this is one of those things, I'm not going to test you on it, but it's one of those things where it's becoming, sort of, it's a big deal for being able to, this you need if you're looking for things like stereochemistry. If you want to know which enantiomer do you have. The other thing, so it becomes important, particularly when the molecule gets big, stuff like that. And so what you can do is you can actually run these like crazy sort of, it's used what's called the nuclear Overhauser effect. Overhauser's at Purdue. With that, so he discovered these effects, and so you can do these crazy sort of acronyms. So COSY, this does hydrogen-hydrogen correlations, and so if you put the you run this as using computers and stuff, you put the the signals like this, and what would actually happen is when you run this, the things that are off of this diagonal you can know. So this signal here is a combination of that one and that one. So this signal, so that means these two, the hydrogens from these 2 signals must be right next to each other. So these 2 signals here, right, correspond to there, and they also correspond to here. So that means that these two things correspond to each other. So we know this guy and this guy are next to each other, and we know that this guy and this guy are next to each other. So like that, and so then, and this guy must be all alone, so like that, because it's not correlating with anything, or actually it's the OH, but so like that, and so you can sort of see what is right next to each other. Okay? So that you can also do this with carbon and nitrogen, or excuse me, carbon and hydrogen, stuff like that. So here again, you can say like, well, these hydrogens are on that carbon. These hydrogens here must be on that carbon. This one must not have any attached to any carbons, right? That hydrogen must not be attached to a carbon, and then these hydrogens must be attached to that carbon. So you can sort of do these sort of shift over here so they align, stuff like that. So it works really well, stuff like that. So okay, moving on to mass spectrometry. So this is what we need to do to get the mass. All right. So in the NMR stuff, we've been giving you the formula, but how do we figure out what the formula is? Well, we usually use mass spectrometry. Okay, so with that, and so what it's going to do is what you can do is take advantage of the fact that we can do clocks really precisely, as well as make very sensitive sensors. So what you can do is you can inject your sample into this machine, and what it does is it actually puts the molecule into the gas phase, and then the molecule will actually drift into this this beam of electrons. So this is what's called electron desorption spectrometry. This is the sort of older method. We'll talk about some newer methods at the end. So the electron beams, what it does is it actually fires electron beams in there. And when you're trying to get you have two magnets and you're trying to put the north together, right? They repulse. Well, if you fire a negative charge at something, it's going to repulse a negative charge in your molecule, and particularly one of the electrons in the bonds. And so what it does is it kicks off one of the electrons. So now the molecule is down an electron, right? So and so you've kicked off an electron, and so now your molecule has a positive charge. What you do is you then have a sensor at the end that's negatively charged, so it's going to get attracted to that sensor. Okay, and so the ions, they're going to be we'll show you a picture of this. They actually get what you do is as they're going towards there, you make them make a corner, okay, and you put a magnet there, and depending on how much they interact with that magnet, how they get deflected is going to separate them. Okay, so your molecule comes along here, it gets your electron beam, you put your negative charge down here, so it's going to get attracted down here, but as it rotates, does this sort of curve, there's a magnet here, and so it does it shift it a lot, does it shift it a little bit. The least massive get deflected the most, like the little go-kart can take this thing a lot, while the big things get deflected the least, right? It's going to take a longer time. Big semi-trucks doesn't take that curve very well. But then you have a sensor here and a collecting screen, and so you say, how many times have I get, so you have a sensor at 15, you have a sensor at 16, 17, 18, 19, 20, 21, 22, and all the way up, and you just count how many times you get a hit on each one of these sensors. Okay, so like that, and so like we're getting a lot of hits at our 57 sensor. We're getting a few hits at 71. We're getting a few hits at 86. Just a small amount of hits at 87, stuff like that. And so you get this fragment pattern. So it's just relative abundance here. It's technically mass over charge. Now for our molecules, we're really only going to assume that it's a charge of +1. But if your molecule was 86, which is here, if somehow you got two plus charges on there, it would show up at 43. It would show up as this 43 peak. So for that, because it's mass to charge, so it'd be 43 divided by +2, so it'd be 86 divided by 2. So it gets, as the molecule gets bigger, that becomes a bigger issue. It becomes a more significant issue. But for this sorts of things, for small molecules, it's usually just the 1. Now the tallest peak, where we set it at 100, that's the base peak. Doesn't really do a whole lot. So you need to know about it. But the important one is the heaviest peak out here. That's what's called the parent ion. So that's going to be the mass of your sample out here. Okay. The problem is, notice how there's all this. So you say, well, why aren't all of the peaks at this 86? Why aren't we only getting signal here? Well, the problem is, remember when we were kicking off an electron? Well, where are those electrons? You're not going to take a core electron. Those are too tightly bound. What you're going to do is you're actually going to knock off an electron from a bond. So now instead of having a 2-electron bond, you're only going to have one. and stuff like that. And so what happens is that greatly weakens it. So as it's going down that curve, the molecule itself can just spontaneously break apart. Okay, and so now they're not nearly as large, and so they're going to get deflected differently. Okay, so like you could, if it broke that bond, you'd have this fragment. Broke that bond, it'd be this. Broke it here, you'd have that. And so that's why you're getting these peaks here. Okay, stuff like that. And so here, so you say, okay, what's the base peak and what's the parent ion, right? So your base peak is going to be here. It's whatever the tallest one is, and the parent ion is going to be your heaviest peak. And we'll talk about these little tiny things of grass in a second, but this is going to be your parent ion. This is the important one. Okay, so this is your M plus, your parent ion. This is your base peak. Okay, now what those things are down here, these are isotopes. Okay, stuff like that, particularly the ones that are slightly ahead, stuff like that. And so, 1% of your sample is going to be 1 molecular weight larger, because it's either going to have a deuterium in it or a carbon-13 in it, stuff like that. And so that's going to be, so some small fraction of it is going to be, if your sample was, say, 106, some small fraction of it's going to have a single carbon-13. So now it's 107, right? So that's what's going on here, stuff like that. And so, right, so some of these, but most of these are pretty insignificant, right? So you're going to have a really big peak, and then just maybe some grass down here that some small amount of silicon, right? It's got quite a few, stuff like that. For most of them are pretty small. The exceptions are stuff like that. So so it's going to be that small percentage that contains either hydrogen or a carbon-13, usually carbon-13, maybe a deuterium, stuff like that. So how height that is, it's sort of roughly equivalent to the isotope abundance. So that becomes significant if you're talking about chlorine and bromine. Okay, so with that, so for chlorine, almost a quarter of the chlorine atoms are going to be carbon-37 instead of carbon-35, and so and for bromine, half the sample is bromine-79, the other half is 81. Okay, so if you look at bromine, right, half the sample is going to be, so if your molecule is what 10 whatever, so if that's 156, okay, half of them are going to have that bromine 79. The other half is going to have the bromine 81. So it's going to be 2 larger and stuff like that. So they're going to be roughly equal size. Okay, with chlorine, right? It's 3/4 of your sample is going to have chlorine 35 in it, but the other quarter of the sample is going to have chlorine 37. So it's going to be 2 higher, right? Stuff like that. And so it's roughly 1/3 the size. So this is actually a good test. When you don't know what the compound is, if you see this crazy isotope here or this, ooh, I might have a bromine or a chlorine in there. If he sees this and you say, ooh, I've got a chlorine in that molecule. Stuff like that. So those actually work pretty well. The other thing that you can come out with is what's called the nitrogen rule. And it turns out that if you have an odd number of nitrogens in the molecule, you're actually getting an odd mass. It's the only one that really does that, only typical one that does that. Stuff like that. So if you have methane here, right, it's 16. But if you have methylamine, right, you have 1 nitrogen, the mass is 31. Okay, now this doesn't count for this. We're talking about the parent ion here. The fragments can have a negative or have odd numbers. But we're just talking about the parent ion here. But if you have 2 nitrogens right here, dimethyl ethylene diamine here, right? So with that, so you're going back to the even. So if you can have even masses with the with nitrogen. That just means that it's you have an even number of nitrogens, but but if you have an odd number, you're definitely going to have 1 or 3 or 5 nitrogens in it. Okay, so to solve the structure, again, you're going to need a couple of things. Eventually you're going to need to do the DOU, so that after you get the formula. So don't forget about doing that. Okay, but the other thing you're going to want to think about is solving the hydrocarbon part of it. Okay, so with that, so there's actually a fairly simple way of doing this. Okay, so what you do is you start off with how many. So say like, okay, how many nitrogens are in there, or how many carbons are in there. So with that, so what is the maximum number of hydrogens I can have, right? So if I have 4 carbons, Okay, what's the maximum number of hydrogens I can have? Well, it turns out that it's 2n plus 4. So if this is if this is 4, then it's 2 times 4, so 8. It's 10. So if I have 4 carbons, then the maximum number of hydrogens I can have is 10. With 10 carbons, right? So it's 2 times 10, so 20 plus 2 is 22. So I can have 22 hydrogen atoms. Okay, so well, why does that matter? Well, I'll show you. Okay, so if we're going to say what's 132, n plus equals 132, propose a valid structure. Okay, so first thing we got to do is say, okay, we know it's a hydrocarbon, right? So it's only, so we don't know, so it's this, right? So it's some number of carbons, some number of hydrogens, right? So that's taken up into the 132 value. Okay, so if we had, say, I don't know, let's say we had 8 carbons. Okay, what's the maximum number of hydrogens we can have? Oh, excuse me, maximum number of hydrogens, right? Well, it would be let's say so it'd be 2 times 8 plus 2, 16, 18, right? I hope I get this right. Stuff like that. So stuff like that. And so the maximum formula can be is we C8 H18, right? Stuff like that. So that would be 2 times 8. Or excuse me, do the DOU. We have 8 carbons, right? Each of them times 2, and then plus 18 times 1, right? Because that's the mass of the hydrogens, right? So I might be way too high on this. So 8 times this was what? 96, right? 18. So 114. Okay, so, no, that's right. 114. Okay. We can't pack any more hydrogens on there. If we have the 8 carbons, that's the most that we can do. We need to get to 132. Okay. So for that, so the easiest thing to do is then go and say, hey, let's say 9 carbons. So like that. So what if we had? Well, then there the max number of hydrogens would be. Oh, this one was. Right, would be is equal to, well, it'd be 2 more, right? So it'd be, right, so it's 2 times 9 plus 2, right? So it'd be 20. Okay, so that would be C9H20, right? So that's what, 9 times 12 plus 20 times 1. So that's 128. Again, it'd be great if we could just pack on 4 more carbons and then that's 4 more hydrogens and that's it. Well, it turns out we can't, right? Because that would mean that you'd have to add in more. Oh, I didn't realize you can't see this. The carbons would have to have 5 bonds. Okay, so let's start off. Let's say, okay, well, what did we do here, right? We did 10. So that would mean max number of hydrogens equals 2 times 10 plus 2, right? So that's 22. So we had C10H22, right? And if you do the math, it ends up being what? Right? What is it? So it actually ends up being, so each time you go out there, you notice we added 14, so it'd be 128, 14, so 142. This is what the maximum number is. Okay, so what we can do is notice how we have where the maximum number is 132. What we really need is 132. So what's the easiest way to get there? Well, let's just subtract 10 hydrogens. So that means our formula must be C10H12. That's our formula. But that's not what I asked you for, right? I asked propose a valid structure. Okay, so that's where the DOU comes into play. Because this is you can just draw something, okay? But how do you know quickly, if it's right or not? Well, you do a DOU, so it's 2 times 10 plus 2. We don't have any nitrogens, right? Nor any halides, right? But we do have 12 hydrogens, right? So divided by 2. So with that, so this is 10, 22. So 22 minus 12, 2, so it's 10 over 2. It's 5. Okay, so that's all the information I gave you. Okay, so here's the question. So how do we do this? Well, remember this is rings plus pi bonds, right? Now usually 99 times out of 100, if you have something 4 or greater, you're going to have a benzene, right? Because you can start off with a benzene like this, right? So there's a ring, and we're going to put in, what is it, the 3 pi bonds, right? So there's our 4, right? So, and we've used 6 of ours. So let's say I'm going to put in 4 more carbons, right? And then say, hey, let's put in a double bond there. There you go. There's a structure. There's a valid structure, right? So for this, so it doesn't matter what you do as long as you do this. And figuring out the DOU is a really quick way of doing it, right? I've got 10 carbons in here. I've got 1, 2, 3, 4, 5 degrees of unsaturation. It must be valid. Okay, so this is just what we did. Now the question is, like, how did I come up with this 8 number? I didn't. I just pulled it out of the air. But I knew what you really want to do is be slightly below it and then be able to work up to it. Stuff like that. And so it was a fairly large number, so there must be a fairly large number of carbons. So I started with 8. But you can start off with any. If you're really high above it, you may want to dial it back and see where you go from there. This works 99% of the time. Okay, so by that, so all these structures are valid. This is valid. That right. So some version of 5 rings plus pi bonds is going to be a valid structure because I didn't give you any more information than that. Okay. Okay. So gas chromatography, mass spectrometry. Okay. So with that, so you can combine this thing, and this is what's used to analyze complex mixtures. Okay, so what you can do is before your mass spectrometer, okay, what you can do is you can put in either gas chromatography. There's also liquid chromatography, stuff like that. But gas chromatography, what it does is it'll separate out the chromatography separates things out. So what you want to do is think about this. Think about you want to get you have a bathroom scale, stuff like that. So you want to say, and you're at a marathon, okay. What you would do is, if you wanted to get the weight of everybody, of each individual runner, right, it'd be really hard to do all at the, when they're all bunched together at the beginning of the race. What you do is you weigh them as they cross the finish line, right? You just have them cross the finish line and then weigh them individually, and then you get a lot more information about them. It's easier to figure out what goes with what. That's what's going on here. This separates out the different components, and then the mass spectrometry is each component as it comes through the gas chromatograph. It'll analyze that particular peak. Okay, and so what it can do is these guys are getting separated out. They're coming through the chromatograph at slightly different times, and as soon as it comes out the chromatograph, it goes into the mass spectrometer. So this peak. So even though you've got all these little things in here, okay, we can go in and take a look and say, this component here, what's its mass? What's this component? Well, so what this is done primarily for is actually for drug testing. So they extract your urine and then squirt it into a GC mass spec. So by that, and so this one here, right? So that you can tell that they know what the fingerprint, what this should look like in the mass spec. So they look at each one of these components, okay, and then they get the mass spec of that. The mass spectrum of that, mass spectrum of that, mass spectrum, and each one of those, the fingerprint goes through the little database, and then pop, stuff like that. So it knows, ooh, this is THC, this is tetrahydrocannabinol, stuff like that. So this, oh, you must have been smoking marijuana, stuff like that. So it's in there because it comes up, stuff like that. So you come in here, right? So the run itself is only, it's only like 30 seconds long, stuff like that, but you can get these done, stuff like that. So that's what it's used for. So this is, so we talked about electron ionization, stuff like that. So that works fairly well with small molecules, although you do have the fragmentation stuff. But what happens if you have larger molecules that want to do, or you want to avoid the fragmentation, stuff like that. So what you do is you do a softer ionization method, and that's what's called electrospray or matrix-assisted laser desorption ionization, or MALDI. Okay, what those do is those actually, instead of using the an electron to induce a positive charge, what they do is they just add an H+. Right, so if there's a basic component on the molecule, it'll absorb that little bit of acid. Stuff like that, and then voila, it has a positive charge, and then it does the same thing. Now the only problem is the it's because you're adding an H plus to there, you're adding an extra proton to the molecule, and so what you get out is not M plus, it's M plus 1. So if your molecule is 100 or 1,000, let's say it's 1,000, so by that the M plus peak that you get out is actually be 1,001. So by that you have to take that into account. Okay, but you don't get fragmentation, and you can get up to really large sizes. You know, at least 1,000. So if you're a biologist, it's 1,000 Dalton or 100,000 Dalton. If you're a chemist, it's 100,000 grams per mole, or an AMU, stuff like that. And I'm sure you can get much larger than that as well, stuff like that. So the way that moly goes is that you actually you mix your sample with a matrix component. I don't know much about the matrix component, although it assists it, but it does provide that H plus in there, and you mix it together and you put it onto it's a gold plate, stuff like that, and you let it dry, stuff like that, and then you fire a laser at the sample, bang, stuff like that, and that knocks out, it fragments some of those things, and it gets some of those little ions into the gas phase, and there's a little vacuum that'll suck those things up and then go and send it down the mass spectrometer. This works really well, stuff like that. So it's a really nice technique, and you know, lasers make everything better. So there you go. Okay, so just a couple of more examples, and then we'll be done. So with that, so for this one here, so if you have, say, an so draw a valid structure, so with that, so you have an M plus of 86, but I've also put the caveat in that you have to have an alcohol in there, right? So an alcohol is an OH, right? So with that, so you know the formula has to be, there's going to be some number of carbons, some number of hydrogens, and then an oxygen. Remember I said N alcohol group, so there's only one OH. So you know you have one H in there, or excuse me, one oxygen in there. Okay, so for this we know it's basically it's an O1, right? So but we don't know this part here. Okay, but we know that 16 of that is that oxygen, right? So in order to get this part here, we have to subtract out the oxygen. So the 16 from the oxygen, so it ends up being 70. So that's really what we're trying to go for on the carbon and hydrogen part. Okay, stuff like that. And so let's say it's I don't know, 4 carbons. I don't know, I'm just guessing here. Stuff like that. So the max number of hydrogens, right? That would be, remember it's the 2n plus 2, so that would be 10. Okay, so we would be C4H10. Okay, so by that, so for that, right? So it's it's 4 times 12, right? Plus 10 times 1, right? So it'd be 48. This would be 48 plus 10, so 58. Oop, we're getting close. So by that, so that's the max it could be, right? We can't add more because we're trying to get to here, not the 86 to that 70, right? Because we already know that 16 of that is that oxygen. So let's add another one, C5, right? So max number hydrogens, right? So for here it's 2 more, so it would be 12, right? So 2 times 5, 10 plus 2, 12. So that would be C5H12, right? So it's 5 times 12 plus 11 plus 12 times 1, right? So for that, so that would be 72. Okay, so we needed to get to 70, right? So the easiest thing to do would be to just subtract 2 hydrogens, right? So C5H10, right? But that's not the formula. What's the formula? The formula is going to be C5H10O. That's going to be the formula. Okay, so with that, so the but again, that's not what I asked you. I asked you for a valid structure, right? So we do a DOU on this one. So DOU, right? So 2 times 5 plus 2. No nitrogens, no halides, right? The 10 hydrogens, right? Divided by 2. So this is 12 minus 10, 2, 1. Okay, so that means you have a ring or a pi bond, right? So I didn't give you any information other than that. So you could say, hey, let's do a ring, right? A 5-membered ring, right? And hey, let's put an alcohol in there. There you go. Formula. The other way that you could, right? So you could do, I don't know, you do a double bond in there with an OH here. I don't know, you could do here and then I don't know, OH here. I don't know, that'd be 1, 2, 3, 4, oh, and then let's put one there, right? It doesn't matter, right? As long, because that's all the information I gave you. So it could be, you know, you could do a little ring with that. It doesn't matter. You just have to pick one. You just have to draw one of them. Okay, So there you go. Now the other one, I realized we only had the one carbon NMR. So I figured we'd do another one. So C5H10 Br2, right? So your broadband, right? So it's 12.7, 20.7, 41.0, 55.0, 58.1. Okay. So the depth, DEPT-90, we don't have any, so none. For the DEPT-135, right? So positive, 12.7. This is 41.0, and then the negative, 20.7 and 55.0. Okay. Okay. I don't have that. We'd have to look at the chart. So first things first, right? So we have 5 carbons, right? And 1, 2, 3, 4, 5 signals. So you don't have to worry about equivalency. Okay. So we're going to do DOU first, right? So DOU, 2 times 5 plus 2. We don't have any nitrogens. We do have 2 bromines, right? Or 2 bromines. So we have 2 halides, right? And then 10 hydrogens, right? So 2, right? So 10, 12, and then minus 12, right? Equals 0. Hey, that'll work. And because we know that they're all equivalent to each other, right? We know that they have to be in some sort of line. 1, 2, 3, 4, 5, right? Because there's no way that we can do this. Okay, so let's look at the depth stuff. So we don't have, remember, so this is the CH, okay? So the positives, right? So this could be CH or CH3, right? We know that we don't have any CHs, so these have to be CH3 and CH3, okay? For the negatives, we know these are CH2s, so this is a CH2, and then this is a CH2, right? So what's that? Well, it's not in any of the depth ones, so it must just be a C, okay? But we have 2 CH3s, so they're not equivalent to each other, right? So they have to be here. They have to be at our ends, right? That's the only other way we can do that. So then we've got a choice. Okay, so we have 2 CH2s and a C. So we can either do, say, CH2, C, CH2, right? And then put bromines on there. The other way that we could do it is we could do C, CH2, CH2, okay, CH3. And then we'd have to put the bromines here. Bromine, right? Like that. So these would be the 2 simplest ways of doing it. Stuff like that. And so which one is it? Well, you can look at it either 2 ways. Okay, so because we didn't look at the what is it? The chemical shift. So these are the regular alkanes, right? But these are going to be probably near the bromines. Okay, so by that, because this is the only electronegative thing we have, especially since there's no degrees of unsaturation. Okay, so this one is definitely going to be, that's the only place we could put them is on there. But we have a CH2 next to a CH3. So here they're next to the CH2s. Okay, here it's the CH2 next to CH3. So we know it's not that. The other thing that you could look at is that the molecule itself is actually symmetrical, and that these 2 are equivalent to each other, and so are these 2 are equivalent to each other. So we would actually really, on the carbon signal, we only have 1, 2, 3 signals, but we have all 5. Here, each one of these carbons is unique, so we give 5 signals. So that's the formula there. So that's all. I know it's a long term, and thanks for your attention.